Hey class, how you doing? We're taking a look at our very last unit in Business 307 on multiple regression, Unit M, and it starts on page 177. Of course, that's just the title page. Let's go down here to this page right here on page 179, which gives you just a bit of an overview on multiple regression. And really, I can probably do that a little better on the next page. This is we're going to look at the multiple regression model right here, and then how you read the tables, the interpretation of the coefficients in the t-tests. We'll look at the r-squared and the f-test, the assumptions, and then two really important concepts which are something that we really haven't covered in simple linear regression. So this stuff is just really an extension of simple linear regression. But multicollinearity and dealing with dummy variables are two important concepts that we want to take a look at. And they also have to do with a couple of questions on your assignment, questions 2 and questions 4 respectively. So let's take a look then at page 180, M2. I'm not sure how far we'll get in this lesson here, but the title that I'll give that will certainly have the page numbers that we have that we're going to cover here today. So multiple linear regression, it says, whereas in simple linear regression, there's only one x variable used to explain y. In multiple linear regression, we've got two or more variables that are used as predictors. Remember, we're not talking about observations here. We're talking about whole columns of numbers on an Excel spreadsheet. Think of it that way. So we'll be looking here at the price of a house, which will be our y variable. And then what are the factors that go into determining the price of a house? And so one of the variables here then will be the size of the house. Actually, the order that we've got them are shown down here. And so the y is going to be the list of the house, list price. So maybe we should just call it the price of the house, or I guess list is fine here. And then we've got the number of garage stalls here. And then we've got here the size of the house in square feet. And then we've got here the days on market, and so on. We'll take a look at that in a moment here. But this very top one here then is the population regression model. So this is about where we ended with a simple linear regression model, plus the error, the epsilon. But we've got more than one x variable. So there's actually a slope for each x variable, all the way up to p variables. The population regression line is shown by this next one here without the error. And then the sample model, these are the guys that we tend to, of course, be working with. Instead of having betas, we've got b's. So this is the intercept. Here's the slope for the first variable, garages, the slope for the second variable, square footage, and so on. And then we've got an error. And then these are the points on the actual regression line, the y-hats. Now, you're right in that is it really a line anymore? If you have two dimensions, an x and a y, then you have a regression line, which shows the relationship between them. If you add another variable, so you got an x1 and an x2 and then a y, then I guess you've got a regression plane in a space, and then if you add another variable, it would be a regression space within a four-dimensional thing. And so, of course, you really can't even visualize this thing beyond a couple of variables. But nevertheless, here we have something here which I guess is really multidimensional if you were to graph this. But each variable has its own coefficient or its weighting. And we'll see how that works then in terms of how the x's explain the y's. So these are the variables that we're going to look at. So the listing price of the house will be our y variable. And then these guys here are going to be the x variables. Let me show you the actual data, and we'll see how they look here. So here's the listing price of the house. This is data for a really small town, and it's actually a little old here, but it fits well, and it still serves the purpose well. So I could knock these all up by about $200,000, but we're just going to leave it the way it is. Actually, probably about $400,000. So here's the listing price of a house. So here's one house, and row number 1, this house goes for $57,900. This is the number of garage stalls that it has. This is the size of the house in square feet. The days on market, that was the days that it was listed before it sold. The number of rooms that it has. And a half room has to do with the baths here. So you probably know then that a half a bath then is one that doesn't have a shower or a bathtub. So it just has a sink and a toilet. So that would be a half bath. This is the number of fireplaces. And it turns out actually to be a really important variable. Number of baths. And then we've got something here which we're going to call a dummy variable. Kind of a goofy name for the thing. But what it is, let me just back up here to where it's described. Right here. And it's the type of heating. It's actually how you handle non-interval scale variables here. So the type of heating is 1 if it's natural gas and 0 otherwise. And we'll talk about a little bit later about how you can handle variables that have more than one category. You have to set up a number of dummy variables, but we'll get to that eventually. So in this particular case then, this first house, row number 1 then, is we've got this particular house is heated by natural gas, but you get down here to the 4th house and it's not. This last one here is called a slope shifter, and it will come into our discussion at the very end of this unit about dummy variables. And it's just a product here of the dummy variable, natural gas, times square footage. That's a relationship that we'll look at. So when natural gas is equal to 1, then it'll be the square footage times 1 is equal to just the square footage again. And so whenever natural gas is equal to 1, then this variable is equal to square footage. But whenever natural gas is equal to 0, it zeroes out. So that's what the thing looks like. So those are the variables that we're going to be using. And the last two, again, just kind of stick away for a while until we get to the end of this particular unit. I just want to go down to the very bottom here and take a look at some of the stats here, so the means and the maxes. So here's the house sizes that we're talking about here. And they run anywhere from, well, the lowest is 860 square feet up to 4,000. So really that's the applicable range. I mean, we can look a little bit outside of that, a little higher, maybe a little lower. But practically that's our range here. So you can't really talk about an 80,000 square foot house and come up with an extension of the regression line all the way out to there. We talked about that in the one of the last units in Unit S. And similarly, you can't talk about really using the regression line to estimate a 200 square foot tiny home. The average size is 1,806 square feet. So our estimate that we get from the regression line is going to be best around that area there. Okay. What else do we got here? Fireplaces. So we'll be taking a look at that one. That'll be an important one. Minimum is 0, maximum is 3. So again, we can't really be talking about houses with 10 fireplaces. It doesn't work that way. And that's about what I want to show you. Here's the range for the Ys. So we got house prices that go from 38,000 up to 269,000. So maybe a very small little town and maybe a few years back, but the average is 74,000, which is probably about 400,000 less than it is now in Red Deer. So that's the model that we're going to be looking at. And again, this variable right here, which is our listing price, is our dependent variable, our Y variable. And all of these guys are X variables. Okay, so the study attempts to answer the question, what are the factors that determine the listing price of a house? All right, and so we're going to be using the variables which we just talked about, and we're going to run the regression, and here's what we get when we run the full regression on all of the variables except for the two at the end, which were the dummy variable and the slope shifter. We'll talk about those later. So over here, over here, there we go. We see the different variables there: garage, square foot, days, rooms, fireplaces, and baths. Remember that in the labs videos section on instructional videos, it will tell you how to actually run the regression using Excel. So I'm going to assume that you've watched that and that you can get this output here. All right. Notice that I'm not showing any standardized residuals. We only did that when we were looking at eliminating outliers, so we won't be handling that here. But let's take a look at what we've got here. And the unfortunate thing is the way that the manual is set up is there's a bit of kind of back and forth here, so I might be scrolling up and down a little bit here to show you these particular values. But let's take a look at the first part here. It says, write the equation for both the sample regression line and the sample regression model. So here's the coefficients that we have right here with their variables right over here. So the way that we would write this then is the model looks like this. The actual listing price of a house is equal to minus 1862.91 is the intercept, plus 958.65 times garages. And I'm just going to use, instead of X's, I'll use just the names or a symbol for the variable. Plus 30.17 times SQF, plus 14.80 times days, minus 222.84 times rooms, plus 12,365.57 times fireplaces. And here, I'm just going to drop down here. This is an extension of this line, plus 4620.38 times baths, plus E. There we go. There's an E. Oh, no, not plus E. This is the model. These are the actual list prices. And then the line here is going to be exactly the same, except that these are the fitted values, the values on the line. No, this is plus E, isn't it? Plus the air term. Sorry, it's getting late in the day. And the actual values then on the line is minus 1862.91 plus 958.65 times garages plus ... plus 4620.38 times baths. And that's where we end, because these are the points on the line. So remember, the difference between the model and the line is that the model are dealing with the actual list prices. So that would be, if you go back here to the data here, I'll go back up to observation number 1 here. That's this guy, 59,000. And then if you plugged each of these numbers into the equation, we would get the y hat value, or the list hat value for row number 1. And the difference would be the air. So I'm not going to go through that calculation, but that's what we would do. And go back and take a look then in Unit S, where we walk through an example of that. So that's what we've got. Let me just kind of clean this up a little bit here and put down again for the model. This is plus E, but you don't have that for the line. All right, let's look at the interpretation and testing of the coefficients here. So I'm going to get back to this paragraph here when we take a look at actually answering these questions here. So, considering the output for regression number 1, what's the meaning of the coefficient of SQF, and what's the meaning of the coefficient of FP? So let's go back up here, and we're talking about then these coefficients right here. So square footage and fireplaces. Okay, so holding that in your mind, or you can scroll back up there. What we have here then is for square footage, that coefficient there was 30.17. And that is the price per square feet. So we're saying then that for every one square foot increase in size, price increases by $30.17. Now, I'm going to add a term in here, which is right there. And I'm even going to put that in a different color here. With all other variables held constant, at their mean. Okay, and we're going to talk about what that means here in a moment. For fireplaces, then that number turned out to be, what was it, 12,365.57. And so we would say then for every additional fireplace, price increases by $12,365.57. Okay, with all other variables, I won't write this whole thing out though, with all other variables, ... held constant at their mean. We'll see what that means when we get down to the next problem, to the next question here. But I do want to just stop here for a moment and say, this sounds like a great deal. Because how much does it really cost to put in a fireplace? Well, under $5,000, right? Even if you get a fairly good fancy one and so on, it's under $5,000. And so this is a great deal. You can just keep stuffing fireplaces into this house. And the price of the house, the listing price of the house, let's say that's the value of the house, we'll just call it the price, will increase by $12,365. And again, that's where you look at this and you say, yeah, within a certain limit. I mean, the highest number of fireplaces that was in the data set was 3. And it was actually only a small number of those. So you're really talking about the difference between 0, 1, and 2 fireplaces, and with the odd 3 there. So you can't just put in 8 fireplaces in a house and expect it to go up by 8 times $12,000, about $100,000. It doesn't work that way. It's good within a range. Now, this whole thing about being held constant at its mean has to do with the coefficient of rooms. If you take a look at the coefficient of rooms, it is minus $222.84. And the question is, why would it be negative? Wouldn't you expect that the more rooms that you have in the house, then the higher the listing price of the house? And the answer is, yeah, but that's because the more rooms that you have typically means a bigger sized house. But this whole thing about holding variables constant at their means means that when we have measured the size of the house and it's in the regression model, then we hold it constant at its mean, which is an average house size of 1,806 square feet. That was the mean for that variable. Now what happens when you start stuffing rooms in? Well, they get smaller, right? So without changing the size of the house, then you would find that there would actually be a negative effect on the listing price of the house, right? So I'll just put that down here in terms of as size is held constant, at its mean of 1,806 square feet, then as we add rooms, they get smaller. And that, of course, has a negative effect. If size, square footage was not in the model, then all of that information is kind of included in rooms. So if we were doing a simple linear regression of just one x variable, and that would be rooms, what you would find out is that it would be highly significant and highly positive. And that's because, of course, as rooms increase, so is the size of the house. But when we measure that, hold it constant at mean, then this is the kind of thing that we end up with. So that's why we call these particular coefficients here partial regression coefficients. They're actually dependent on the other ones being held constant at their mean, and what would happen if you just increased that particular variable. Now, because of that, when we get into doing hypothesis tests for the coefficients, we always do them as two-sided tests, and you'll see the p-values are always two-sided tests, and that's because of the interaction of the x's with each other. So again, commonsensically, we would look and say, well, rooms should have a positive effect then, a relationship on the listing price of the house, but when it's in the model with size, it actually turns out to be negative. So that's why we always do these as two-sided tests, because of that interaction between them. Whenever you see this question here, which of the 6 explanatory variables are individually significant in explaining the listing price, then we're talking about individual tests. And I want to go back up here. And if you watch the lab video, I made a to-do about this. But here I want to talk about this in your notes and say, if I was to draw a line here, this actually divides, this divides the table, the regression output, into 2 different parts here. The stuff above the line is dealing with aggregate tests and measures. The stuff below the line is dealing with individual tests and measures. Individual, can't get that last couple of letters, I'm too close to the edge there. Individual. So when we ask this question down here that says, which of the 6 variables here are individually significant in explaining the listing price of the house, we're looking at the bottom part here. So the stuff below the line. Now, let me show you how you read this. This is also, again, talked about in the lab. These are your B's, BI. So this is your B naught, your intercept. This is your B for garages. This is your B for square footage, and so on all the way down. These are your SBs. So this is your SB naught, which we calculated by hand in a simple linear regression. This is your SB for garages, your SB for square footage, and so on. If you divide the B by its SB, you'll get the T star value, which is what these guys are. And then we can calculate a P value from that, and it's always a two-sided test. And then finally, we can come up with confidence intervals, which we calculated by hand. And so this shows you then, let's take a look at the intercept. And the intercept then has a t star, which is minus 0.15. That's a p-value of 88%. This is actually pretty close to the middle of 0. And so this is highly insignificant, not significant, right? Very high p-value. If you take a look at the range here for doing a confidence interval for beta naught, right? So this is a confidence interval for beta naught. We're saying that we're 95% certain that it's anywhere from minus 26,700 to plus 22,900. So that's an interval that has a negative lower bound, a positive upper bound. It contains 0. That means that this is not significantly different from 0. If you go down and take a look here at the p-values, the only two variables that actually have p-values which are significant are square footage and fireplaces. All the rest are really high, and they correspond to low t-values. Oops. So low, 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 low. And a high t star means it's way out in the tail, a low p-value. This is high. This is a low p-value. Take a look at the confidence intervals for those ones which are significant. So anywhere from plus 18.95 to plus 41.38. Two positives. Doesn't contain 0. Down here is talking about for fireplaces, anywhere from 4,800, positive 4,800, to positive almost 20,000. Okay, but all the other ones have a negative and a positive for a lower and an upper bound, so they contain the 0. So let's just take a look then at, we're going to formalize our tests here, and we're just going to focus on these guys here. So let's go down here then, and we're going to do the hypothesis test. Now there's actually 6 different hypothesis tests that we're doing here. And so the first one here then is, actually I'm going to do them all together. So HO is that the beta for the ith variable is equal to 0. For all variables where I is equal to garages, square feet, what do we got? Days, rooms, fireplaces, and baths. So those are the different subscripts. Against the alternative, remember these are always two-sided tests that are not equal to 0. So that's step number 1. Step number 2 is that this is a T star formula, is equal to the beta sub I value, where I is garages, square footage, etc., over its SBI value. And then let's take a look at a critical region here. So here's a T. And the degrees of freedom, just like in simple linear regression, is n minus p minus 1, but the p now is equal to 6 explanatory variables. Our n is equal to 90. If you go back and count all of those observations, then you'll end up with 90. I think they're actually numbered anyways. Let's just go back there. Yeah, so we've got 90 observations here. Okay. Now, here's the trick. You can always find n minus p minus 1 as the degrees of freedom for SSE. So that is, let me just change colors here. SSE is right here. So here's SSE, and another name for residual is error. And so we've got 83 degrees of freedom. So that's what you can use for the individual t-tests, n minus p minus 1. So that's 83. And if you look that up on a t-table, it nicely turns out to be plus or minus 2. That's with a 95% level of confidence, 5% level of significance, so 2.5 in each tail here. So plus 2 and minus 2. All right, step number 4 is we're going to look here then at, let's just build a little table. Oops, I got a thick one there. Well, that's okay. So we're going to have the variable, and then we're going to have the t star, and then we're going to have the p-value, and then we'll have the decision. So let's take a look at each of those. So the variables then that we have are garages. So we're not doing a test here of the intercept. We're just going to do it for the individual variables. Garages, square footage, days, rooms, fireplaces, and baths. Here's the t star values, and I'm just pulling them straight from the table here. So this is 0.30, 5.35, 0.38, I think that is, minus 0.11, 3.27, and 0.91. And the corresponding p-values are 0.77, again taken just straight from the table, 0.00, let me just clean this up a little bit here, 0.73, 0.92, 0.00, and 0.37. So the decision then is that this guy here and this guy here are your significant variables, right? 5.37 is somewhere way in here. So we're talking about 5.35 is over here, and 3.27 is also in the upper tail like that. They correspond to low p-values. And so the decision here would be to reject HO. Whereas over here, the answer is do not reject HO. Not. Okay? So remember that these are actually 6 separate tests, but this is the 5 steps that we have in each case then, and I just put them all together here. So that shows you your 2 significant variables. Okay, I think we're going to stop there today. We will pick up the F test next time. So we went from M1 up to M7 today. And I'm going to conclude that here today. Thanks for listening.